Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to continue our discussion about RNNs. In previous session we talked about the training of RCNN and RNN and how, let me to just have a quick recap. And so in RNN we had something like this. So this is the input and we had the state to produce the output. If we unravel or unfold this RNN through time, we have something like this: x0, the initial state, the output, and so on. Okay, so and we saw how we could calculate the error by summing the difference and getting the loss function or total error function. Now we want to know to discover a little more about the training of this RNN. So the total error is actually the sum of all errors. So in backpropagation, when we want to calculate the derivative of total error with respect to the W, which is the weight matrix, then we could actually write the error as the sum over all time steps of errors. Okay, so at each time step we have an error, so we just sum and add them up to get the final error, and then to calculate the derivative we could actually put the derivative in this sum, in this summation, and as you could see here, this is what we should calculate in the backpropagation. Okay, now let's use the chain rule that we know to get some interesting result. We know that for the time step t, for a specific time step, we could write the derivative of the error with respect to w as the sum over all k's and the derivative of errors with respect to the output in the time step t, and we have the derivative of the output at time step t with respect to hidden state at time t, and then we have the hidden state at time t, we have the hidden state at time k, and so on. And this term itself, actually we could write this, because we have this kind of architecture, so we have h0, h1, and so on. So we could write this derivative as the multiplication between the derivatives of hidden states with respect to previous hidden state. So in that case, because we use the same WHH, if you remember that, so we could write and calculate the derivative, and we could actually calculate a bound for the norm of this derivative, and this is actually less than beta w times beta h to the power of t minus k. And what does it mean? It means that it depends on beta and how much this term could grow or vanish, in fact. So this thing could be really large or really small. So in that case, we have vanishing or exploding gradient problem. So because we multiply the same matrix at each time during the forward propagation, then based on the eigenvalues of this matrix, we could have vanishing gradient problem or exploding gradient problem. So in the vanishing gradient problem, it could cause that the RNN is not able to get the long-term dependencies. For example, let's say we have this example. Jane walked into the room, John walked in too, it was late in the day, Jane said hi too. So probably the network has some problem with filling this blank, because these are really past or really far when we want to train the network, because we have this thing, these words after the network that we want to pass to the network, and so in here the network does not have enough memory to remember the John. So in vanilla RNN, we could actually show that with the RNN block with a nice figure or nice block diagram. In here, as you could see, we have x of t, we have the previous hidden state, we stack them together, as you could see in here, and then multiply them by w, which is the result of stack of WHH, which is related to the hidden state, and WXH or HX, which is related to the input, and then apply tanh or tangent hyperbolic on both to get the current hidden state. So when we have different inputs in the different time steps, we are having this kind of architecture when we unravel the RNN through time. So in this case, if the largest singular value of this W weight matrix, which is the weight matrix, is, so the singular value of this W, if it is greater than 1, then we have exploding gradient when we have lots of these units in time. So in other words, if we have lots of time steps, and if the largest singular value is less than 1, then we have vanishing gradient problem, which probably result in poor memory or poor recall of the RNN. Okay, so the trick for exploding gradient problem is actually a simple solution by Mikolov, is that to clip gradients to a maximum value. So we set a threshold, and then when we calculate the gradient, we could check that if the norm of this gradient is greater than a threshold, then we just make the norm of this gradient unit, and we just take a unit step in the direction of that gradient. Okay, and although it sounds like a very trivial solution, but it makes big difference in RNNs. So in that case, let's say it is a gradient clipping intuition. So when we don't have when we don't clip the gradients, we may have this kind of going backward when we are in here. But when we have the clipping gradient, as you could see, the backward step is really less than this normal step, so we could again reach to the minimum. So for exploding gradient, we could use gradient clipping, and if we have vanishing gradient, we know that we could change RNN architecture. So for vanishing gradient, one thing is use good initialization, or using initialize the weight matrix with identity matrix, and set the activations as ReLUs. So in that case, the experiments show that we could have higher accuracy than normal RNNs, okay, to use initialization and ReLUs as the activation functions. But another solution is to use other hidden units to compute compute the output. And so instead of having a simple RNN, we want to use another units. So we have two major unit and famous one, which one of them is LSTM and then another one is GRU unit. And so the main ideas is we want to keep around memories to capture long distance dependencies. So in that case, we want a network that could capture the long-term dependencies. We have seen an example from the network that could forget the long-term dependencies. So we want to have that long-term memory, and also we want to allow error message to flow at different test strengths depending on the inputs. So based on the input, we want to have an error message flow. Okay, let's see the LSTMs. So the LSTM is the abbreviation for a long short-term memory. So let's jump into them. So in standard RNN or in vanilla RNN, we have this kind of structure to or this kind of block diagram for determining the hidden state. So we have the input and we have the previous hidden state, and we apply the tanh with, so we apply some weights matrices to these inputs, and then we apply tanh to these inputs to get the new hidden state. Okay. Okay, so in LSTM, each block has this kind of architecture. So now we want to discover what this architecture can do and what characteristics this architecture have. So when you see these sigmoids, they are kind of valves or gates in this cell. So they could, because they are between 0 and 1, they could control how much of the input they could pass through the output, okay, because they are between 0 and 1. So they are kind of gates or valves that let the information pass through them. Okay, let's see. So in here at the top we have a linear history. So we call that cell state. So in fact, this the information in this line is only affected by gates. So we have this gate in here, and so the information is only affected by this gate in here, and this gate. Okay. And as I mentioned, gates are simple sigmoidal to control the output of the unit and determine how much of, so let's say this is x, they could control how much of x go through, pass through this line. Okay. Okay, so the first thing in LSTM block is we have is forget gate. So we have x of t, we have the previous hidden state, we pass them through a sigmoid or a gate, as you could see in here, and it actually determines that how much information they want, the cell want to carry over, or how much it want to forget the past. Okay, because we are applying this on previous hidden state and the input. Okay, and also this is an important point, that we are distinguishing between the cell state and hidden state, but they are actually related, so they are not fully independent things, but we are just splitting them, and they have different characteristics, so we name them different things. Okay, the second thing is input gate. So in input gate we have the previous hidden state and the current input. They pass through a sigmoid that now we know how to think about this sigmoid as a valve or gate to produce some output between 0 and 1, and then we just multiply them by the cell state, or it is not in fact cell state, it is C tilde, which is in fact a perceptron unit applied on hidden state and the input. Okay, so we in fact first we apply or create a perceptron for the input and hidden state, or for the information that we have, and then we determine how much of this information we want to have or carry to the cell, or worth to remember. And after that we have memory cell update. So for the update the cell, the C of t is equal to, so now we have f of t, which is just we multiply that with, which is the forget gate output, we just multiply that by the previous cell state, because it determines that how much we want to forget from the previous cell state, and then we add it with the input gates times this, in fact, kind of that perceptron output or potential new cell state. So we want to know, based on the output of input gate, we want to know how to blend these two to create the new cell state, how much information we want to throw away based on the output of forget gate and how much information we want to input to the solid state based on the input gate. Okay, so in here we could see a summary of these relations that you could take a look at. Okay, so again, the forget gate look at previous solid state and current input and decide how much information to throw away. We see that in that block diagram. Okay, and we know the other things that we talked about it. Okay. Maybe a problem in this kind of cell is the peephole connection. So because we have this kind of connections, in this case, the raw memory itself that is come from the previous cell state, it could be information itself and act as an information itself, which could be a problem for the network. Okay, so in here you could see the code for that, which is not really important now, but an important thing in the LSTM is this block diagram. So as you could see here, now we somehow solve the gradient vanishing problem. So because now we have this kind of path, which is an uninterrupted path, and let the gradient to back propagate through the network through a pass without much change in this pass. Okay, so now we don't have vanishing gradient problem anymore. So because we could, the gradient could flow through the network in this uninterrupted path. So the idea of this is kind of like the resonance. So if you remember in resonance, the idea to pass the gradient to the first layer was to use these shortcuts. In these shortcuts we saw how the gradient could flow to the first layers without any change, and that was so good for vanishing gradient problem. And so this is a similar idea to the resonant idea. And there are some more simple versions of LSTM, which in fact one of them is gated recurrent unit, or GRU, which is maybe a little less popular than LSTM. But so in this case we don't want to maintain compressed and regular memories, and so we just have an update gate and reset gate, and so we have a memory and final memory. And now as you could see, we have z of t in here, and we have 1 minus z of t in there. Okay, so maybe it makes more sense to look at the GRU as the units with long-term dependencies have active update gate z. So now based on this diagram, you could see that how GRU could perform. So it is a simpler version of LSTM, and And also there are other RNN variants that, but we don't want to talk about them because the thing is that many of them perform about the same, so we don't want to actually worry about LSTM or GRU, and they are perform much better than vanilla RNN. So if you want to build a model for sequence prediction, you could use these units to build your RNN. And the LSTM in fact used in many areas, for example image captioning, traditional NLP tasks, neural MT, and so on. So they are kind of really commonly used building block for RNN architecture. And if you remember, we talked about multi-layer RNN. One of the things that I want to talk about it is bidirectional RNN. So sometimes we don't have just this kind of relation for the inputs. So let's say we have a sentence. We both could have this kind of relation and this kind of relation. So in that case, we could use bidirectional RNN, and also in images we could have this kind of relation. Okay, so in this case we could use bidirectional RNN architecture to process inputs in both ways. So in here we could see a bidirectional a bidirectional RNN architecture, and the concepts are pretty similar to the RNN itself. So we don't want to go through all of that. So now we know how we could use RNN, and we now know about LSTM and GRU. The most important thing is you should apply LSTM instead of RNN when you want to use sequence prediction. And we will see some examples in RNN and how to use them in Keras. So yeah, that's it for this session. So see you in the next session. Bye.